Welcome to Module 29, Integration, Network Resilience, and Supervisory Boundaries. Integration can improve visibility and coordination, but it also creates dependencies, right paths, timing problems, and cybersecurity exposure. The first question is not which protocol to use. The first question is what operational purpose requires information to cross this boundary, and what should happen when that information is missing, stale, invalid, or rejected. By the end of this module, you should be able to define an integration purpose, classify interfaces by authority, write a basic data contract, manage quality and freshness, and preserve local fallback. You will also learn why external rights must be governed and why communication failure and recovery must be tested like any other functional requirement. The core concept is that integration is an engineering boundary, not only a protocol connection. A poorly controlled interface can make a local system depend on a server, cloud service, or enterprise platform that was never intended to protect equipment. A strong interface is defined, bounded, observable, and recoverable. Higher layers may coordinate, but required local safety and control must remain available where the design requires it. Interfaces have different risk levels. Monitoring reads status, alarms, measurements, and diagnostics. Advisory systems recommend actions for human approval. Supervisory control writes bounded set points, schedules, resets, or mode requests. Direct control commands physical outputs or safety-related behavior. Risk increases as authority increases. Use the least authoritative interface that still satisfies the operational need. Every exchanged value needs a data contract. Define the source owner, units, scaling, range, resolution, update interval, quality, freshness, fallback, write authority, and audit requirements. A value of 55 without units, source, timestamp, and authority is not a complete interface specification. Enumeration is also critical. If one device uses one to mean run and another uses one to mean stop, the integration can fail dangerously. Local autonomy means that the failure of a higher layer has a predictable, bounded effect. Supervisory systems can provide schedules, resets, analytics, reports, and operator views. Field controllers should maintain local loops, proof, safeties, timeouts, and fallback where required. Factory equipment controls should preserve internal protections. Loss of a server should not automatically remove required local safety or equipment protection. BACnet and other protocols do not solve engineering by themselves. Reliable integration still requires governed device instances, network numbers, routing, broadcast management, object mapping, priorities, time behavior, security, and ownership. Large unmanaged flat networks can reduce reliability. BAS, IT, and OT teams must define who owns switches, firewalls, certificates, monitoring, backups, and incident response. External writes need governance. An analytics platform should not write directly to a Valve output when the operational need is a bounded reset request. The local sequence should apply constraints, preserve safeties, expose the active reason, and reject invalid requests. Writes should use role-based access, approved source systems, bounded ranges, rate limits, expiry, fallback, and audit trails. In the worked example, an analytics service recommends a supply air set point of 48 degrees Fahrenheit, but the approved BAS range is 52 to 65 degrees. The local controller should reject or clamp the request, retain the prior approved target, set an invalid request diagnostic, and continue local safeties. The network write may have succeeded, but that does not prove the value is valid engineering control. Failure and recovery testing are essential. Test loss of server, loss of network path, stale values, duplicate identifiers, time drift, restoration, and conflicting writes. Confirm that local control continues, alarms are meaningful, queued commands do not apply unexpectedly, and authority returns predictably. Recovery can be more disruptive than failure when many commands or schedules apply at once. Maintain an integration register. It should list every external system, business purpose, data direction, write capability, owner, protocol, credentials method, firewall path, fallback, and recovery test. Unknown integrations become operational and cybersecurity debt. A current register helps the team understand what depends on what before upgrades, outages, and incidents. Integration reliability depends on IT and OT coordination. Network segmentation, remote access, service accounts, certificates, firewalls, routing, backups, logs, and incident response all affect BAS operation. Security controls should protect the building without making troubleshooting impossible. The goal is not isolation for its own sake. The goal is controlled, recoverable, auditable communication. Common mistakes include choosing a protocol before defining purpose, mapping values without units or freshness, allowing direct output rights from enterprise systems, depending on a server for local equipment safety, using large unmanaged broadcast domains, failing to document infrastructure ownership, accepting a successful write as valid control, and testing network loss without testing recovery. Integrate through defined, bounded, observable interfaces. Let us summarize. Integration starts with operational purpose. Interfaces range from monitoring to direct control with increasing risk. Every exchange value needs a data contract. External rights must be bounded, authorized, audited, and visible. Local fallback must preserve required operation when higher layers fail. For your field prompt, select one integration and document its purpose, data contract, fallback behavior, and recovery test.